Okay, so welcome back. Let's start our afternoon session. Our speaker is Dimitri Gangardt from Birmingham. He's going to tell us about emptiness formation in polytropic quantum lattices. So please start.
So, hello everyone, and thanks for coming. And I'm also very grateful to the organizers for letting me come in here and be in this workshop, which is incredible mixture of different ideas from different areas. And I'm going to talk about my recent work in collaboration with Shushung Ye and Alex Kamenev from the University of Minnesota, which we recently published in this special issue of Journal of Physics A. And the title is Emptiness Formation in Polytropic Quantum Liquids. So it falls nicely in the framework of this maybe last week thematics. Essentially, it has a lot of connections with lineage shapes and tangent methods. So I'm trying to explain it to you in this talk. But first, I have to explain what is emptiness formation and what is polytropic quantum liquids. So let's start with a simple example It's a work done by Sasha Abanov, who was here a couple of weeks ago. And the problem is like that. So imagine like you have a free fermions moving on a one-dimensional line. And one asks, and the fermions are in the ground state, zero temperature. And one asks, what is the probability to have an empty interval of the size 2r from minus r to r, while maintaining the average density at infinity being rho 0. And the quantum mechanical answer to this is given by this nice integral. You take just the ground state wave function and integrate over all the coordinates outside this interval. Well, it looks easier said than done, because of course this function is a horrible determinant, even if it's probably the simplest integrable system. And one have to find an efficient way to calculate this quantity for sufficiently large in certain asymptotic region of the emptiness size R. And this is how it can be done. And essentially it goes back to this morning session. It's done by Instanton calculus. First of all, we formulate the same quantity as the following path integral. One imagines that the ground state can be projected onto by evolving for sufficiently long time, which will be taken to infinity in the imaginary time, and project to the empty interval, which I denote here by the state, this projection to R. So you see that we have some kind of evolution from somewhere in the distant past to something which I consider to be time equals 0, and then back to the distant future. And this can be by using hydrodynamic description, namely my degrees of freedom will be coarse grain density and currents of the fermions. And I have to find the appropriate weight to weight my path integral. So this is my path integral weighted by the action S. And the very important bit here, which unfortunately my notations is not very great, is this point here that actually I require my particle to be absent in the interval from minus r to r at t at tau equals 0. Probably I made it more clear that this is a very important ingredient in this story. So path integral, hydrodynamic action, essentially I write made of two terms. One is represents the kinetic energy of the particles, and this is the same for all Galilean system. And the the thing which characterizes the system itself is this term here, which is the internal energy related to the pressure. And all I need to know is the relation between the pressure and the density, so the thermodynamical equation of state. So for free fermions, this problem was considered. In this case, pressure is cubic, is a power law, which is a cubic power law for of the internal energy, and the equation and the solution was found by Abanov in 2003. What is important that all this integral is dominated by a single configuration. Here you can see the shape of this configuration in terms of the optimal density in the x and tau plane. So if looking from above, that looks like that. There is a region when density is strictly zero, and this region extends from tau equals to 0 to some finite interval in the imaginary time. And the reason is very simple. Particles have some sort of rigidity, and if there is a zero density here, it will persist for some time along the imaginary axis, and this time can be estimated to be something like this size divided by the typical velocity of the particles, which is in turn is also related to the density. And overall, this density is the action can be estimated more or less like the area of this empty figure here, which has the, by the way, the boundary has the very nice expression in terms of the asteroid curve. And as you see, it scales like the size of the emptiness squared, which makes the probability or the formation of the emptiness extremely rare event, like the one which you essentially never seen, but it was described in the mythology. If it's not clear, this is the Moses and this is the Red Sea parting and the Jews going, and the fermions represent the Red Sea. Right. So the typical this typical behavior is what one expects in any decent sort of compressible fluid, and there are some previous results which falls into this category: the random matrices, spin chains, and even weakly interacting Bose gas. In all the cases, the hydrodynamics is a reliable method to calculate the emptiness formation if the size of the interval is the largest length scale. And the problem, namely, the one can think about two scales like that, the inverse, the distance between the particles and some correlation length if it's different from the distance between the particles. For the free fermions, it's the same length. So our talk is essentially trying to extend this calculation to the case where the equation of state is the power of the density. Now, in quantum systems, I'm not aware of any true description in this form, apart maybe from the Lieb-Liniger, which in some extreme cases for small densities, where it becomes free fermions, or large density when it becomes almost free bosons, follow this law, but not for all density from 0 to infinity. So this is, however, an interesting calculation, because in this case, one finally succeeds in calculating this prefactor. The scale, this form will remain the same. Our main achievement here is to calculate this function, which is prefactor of the action, which depends on the polytropic index gamma. So there are two known values. As far as I know, one is the result for free fermions, where f is pi over 2. Also, this is true for the GUE ensemble of random matrices, essentially for every ensemble of random matrices. And also recently, Alex and his PhD student Shishun were, well, this is the wrong number here. Probably, yes, the future boundary conditions are somehow will be important here. So that's probably the case. succeeded in calculating essentially numerically this prefactor by solving the imaginary time version of Gross-Pitayevsky equation, which happens to be AKNS equations. So we want, and this gives, so I can essentially flash the main result right now, because this is the function we have obtained. So there is a nice analytical form as a function of gamma, small gamma, and the function gamma of small gamma. And this is a nice and smooth function, which goes very well with the known analytical results at gamma equals to 3 fermions, and gamma equals to 2, which is this analytical, numerical result. And there are two other points which were obtained. I will tell you how later. But the dashed curve is the analytic function. Now, this is a nice result, but however, what is interesting here, not the result itself. Probably there is nothing, no any features, no phase transition, nothing, but rather how this result was obtained and what is the structure of the dominant contribution in this case, similar to the, yes?
Yes, maybe you said it, I missed, but what kind of real physical system values of gamma, say 1.5 or 1?
I don't know. So I'm not aware of any physical system like that. I will come to this. It's essentially using our solution as well. So we don't simulate. So it might be simulating the hydrodynamical equations, like, but this is not what we've done. Oh, it's yes. So psi is defined as from the thermodynamics as something like inverse sound velocities. Yes, there is a prefactor of it, so it does depend on gamma. Yeah. Right. So okay. So we are now have to find the optimal solutions. The equations of motion, which comes from this action, are standard hydrodynamical equations of motion. First one is a continuity equation. The second one is the imaginary time version of the earlier equation for the velocity, and gamma sits here. And what is important, as this is a simple first order differential equations, the initial problem can be easily solved, but here we have precisely the problem of boundary conditions imposed in the future and in the past, and one have to sort of, even knowing that, find a kind of optimal profile for the density and velocity at tau equals 0, such that going backwards and forward in time, it will smooth down and calm down to the mean density and absence of any velocity. Okay, so there is a well-established machinery how to do that. One can define the Riemann invariant, some complex combination of velocity and density. For free fermions, they are the same, but here one have to distinguish them because they are not the same. Essentially, the W is the linear combination of lambda and lambda bar, and vice versa. So we have two coupled nonlinear equations which we have to solve for the Riemann invariants. For the free fermions, that would be simply two complex conjugate Berger's equation, which can be then each of them solved separately by known analytical method of analytic function. I will come to this a little bit later. So there is a beautiful transformation actually, which allows to transform these equations from the nonlinear to linear. And the idea is, instead of using x and tau as variables and look at the dependence of the lambda and lambda bars, so the Riemann invariance of them, it's rather to invert two functions of two variables to consider x and tau to be functions of lambda and lambda bar. So this is the form of these equations. And what is important, this equation now, what one gets, this equation now become linear equations, still coupled. For fermions, not. So for fermions, essentially, this is the equation for the characteristic, which can be written like that. And the only problem here would be to find the appropriate initial conditions expressed as derivative of some potential. This potential can be shown to be to solve electrostatic problem, the sum of holomorphic and anti-holomorphic function, and this is the appropriate form of the function in such a way that indeed that's the solution found by Abanov, and this describes emptiness as its derivative goes like 1 over square root of lambda squared plus 1, so it diverges when lambda. So for lambda going to infinity, it corresponds to x equals to 1. For general value of gamma, as I said, this equation are coupled anyway, but the way to deal with it can be found in the book of Anatoly Kamchatny. Namely, one can still try with the ballistic propagation, substitute it back to the equation, and find the condition on the potential nu, which now can be written in this form. So the second derivative is not 0, but is related to the first derivatives, proportional to some number n. N is simple, has a simple relation between n and gamma, but the solutions to this equation can be found in a closed form only for integer n. So for special values of gamma, there is a sequence of gamma going from well, in some limits from 1 to 3 for positive n, and for n equals to 0 corresponds to 3 fermions. So the idea of our solution is essentially try to solve this for integer n, to try to, since we have the solution for infinite series of n with some accumulation point, we can claim that our solution works for every gamma by analytic continuation. That's how this result was obtained. So a couple of some technical details here. So the potential can be represented in this form as a finite series. The series, again, are finite only for special values of polytropic index gamma. There is some interesting structure here. So the coefficients have some forward recursion starting from a0 equals to 1. However, the functions have to be deduced from the highest sort of term, working backwards from n minus 1 to 1. So for example, n0 is, as I said before, is the sum of holomorphic, anti-holomorphic function. For n equals 1, the potential is given by this ratio, still involving some analytic functions here, but divided by a non-analytic denominator. So this is the structure, and then can be deduced for every nu. Now, what are these functions for general n? There are two conditions which allow to find them. The first condition can be seen like that. The particles, it's a schematic story of the particles moving in time. Since the particles evolve and have to avoid this region from -1 and 1 in my rescaled coordinates, they will pile up near the boundaries of the intervals, and then the density should diverge there. In terms of in terms of our equations, when you say x equals to the right-hand side, the right-hand side should go to plus or minus 1 to the values of the ends of the intervals when lambda, the density, goes to infinity. So this is one condition. And another condition, which can be also justified by simply linearizing equation at large distances, when the density is more or less given by mean density, which is 1 in these units. And one can deduce that in this case, the density, this potential should behave when density goes to the mean value in terms of this lambda. This is the value corresponding to this mean density, and should have this square root singularity, which is similar to the one we had for free fermions. So in other words, if one thinks about function lambda of x, it's an analytic function with a branch cut. So this is the full solution for 3 values of n. Once these functions can be found by kind of tedious but pretty much straightforward calculations, and one can solve for these 3 cases the explicit dependence of density on the evolution of density. So this is the case of free fermions. At tau equals 0, they start with a singularity near just outside the emptiness region. Then the singularity, which is in this case 1 over square root singularity, goes to the convergent square root singularity, which persists until it simply disappears, and at the time equals to infinity, the particles don't see any emptiness. So that corresponds to this upper cusp. And similar evolution can be found for different other values of n, or other values of gamma. So they all start with a singularity with a different power law. This singularity also becomes a different power law, but converging as tau not equal to 0. So when they evolve and in the end converge to the mean density. So some insight of this solution can be also given by looking at the region inside the emptiness region. In this case, rho is equals to 0, and the problem simplifies considerably. There's still some dependence of lambda on x, but in this case, since rho is 0, lambda becomes real. It's just velocity inside the emptiness, and one can look at the ballistic evolution inside the emptiness. So what it really describes, it describes the envelope of the trajectories which are tangent to the boundary. And one can calculate this function for all 3 known cases. And we will use these results. And the most important result here is that for free fermions, typical divergence near the boundary. So for example, the velocity goes to infinity as I approach, if I take x to 1. So I need to essentially looking at approaching these 2 points, I deduce that the right-hand side should go to plus or minus 1, but the power law in these solutions is essentially it depends on the index n. And one can deduce this form, and I think that there is an interesting phenomenon here, which I can, this is my take on the tangent method, namely one solves the boundary can be seen in 2 different ways. One is the 1 parameter family of straight lines, and one looks at the envelope of these lines. Or in other words, this equation can be seen as a surface of velocity as a function of x and tau, and this surface has a singularity if one looks from above. The form of the boundary is essentially the image of this surface, so sort of shadow which it leaves. It's precisely how we see things. So was mentioned by Vladimir Arnold that typically we see each other or different objects by looking at those singularities. It's just outer contour of whatever one sees with the naked eye. And the boundary is precisely an object like that. And then it is known that such singularity called folds can meet, and when they coalesce, they create caustics or the cusps. And one example of this, if you take a bottle here, that's suggested to use a milk bottle, but in fact one can use any bottle, and we probably can make this experiment later today. And then you will have and move it around. These 2 folds will coalesce and form a cusp, and the cusp has a universal power law described by some universal algebraic curve. All this construction essentially by sort of optimizing over possible values of velocity to find the proper position of this boundary curve is nothing but saying that the function x of v, which I found using this machinery of analytic functions, and the boundary curve x of tau is nothing but Legendre transform of each other. So if I look, there are two types of cusps. So one cusp, as I said, is a standard cusp here, where the two regions which are full of particles meet at some imaginary time tau. So in this case, the universal behavior of the right-hand side can be simplified, and it follows the standard curve, which can be written as a cubic parabola with a linear term which is changing, and therefore two maximum and minimum coalesce at tau equals to tau c, and that leads to the standard behavior of the power law to 2/3 or 3/2 as you wish. And this is the same as and this is really independent on the equation of state. And the reason for that, in this case, particles, the density of particles is very small, and therefore one can rely on some kind of local free fermionic picture. However, there is another of cusp, which I call hard cusp, which happens at tau equals to 0, near the divergence of the density. In this case, one have to do the expansion in terms of 1 over v, 1 of the velocity. And here there's interesting point that, as I said, the structure of our solution suggests that the next term, which would be normally the same for free fermions, for example, it's simply 1 over v to the power of 3, n equals to 0. And that would, for free fermions at least, that does the same behavior, to the same power law here near this cusp. For different values of polytropic index, it's different, and the power law is changing. So this curve has dependence of the power law on the polytropic index near this hard cusp, and this is how it looks like. And the physical reason for that, of course, that here one cannot at all use the free fermionic picture, and one really probes the interacting equation of state. Right. Yes. So one can also deduce the same manner. One can deduce the universal behavior of the density near the edges, and it also shows the power law, which here depends on the polytropic index. So, for example, when tau equals to 0, there is a divergence with all these blue lines. When tau is not 0, there is a n-dependent or gamma-dependent power laws. Here it's a square root, here it's a 3/2, I think, and here some other power. Now, here I should probably say that it sort of contradicts what I was saying before, saying that free fermions should be seen locally near the emptiness. However, one shouldn't simply trust the polytropic power law. Physically, it doesn't make very much sense to look at this behavior. So this behavior can only be seen at certain scale away from the emptiness, as here the square root singularity should take over for any physically reasonable polytropic, so any physical model, because for small density one should fall back to that's beyond this model, because we really use the, as I said, polytropic equation of state everywhere. All right, so finally, just a couple of words how our solution was obtained. So so this is the structure of the dominant contribution. Of course, in our calculation, it's kind of was a tool. However, if one thinks about some limit shape phenomena, in this case, this is precisely what one is interested in. finally, one have to take our solution and substitute into the action and calculate it on the optimal solution. That it's not a very easy thing to do. However, there is a very smart trick devised by Abanov, which relates the variation of the action with respect to the mean density to the behavior of the density at large distance. And this behavior can be obtained by looking at the higher order, the most divergent term in this expansion of the right-hand side, which looks like that. And this coefficient alpha, this is precisely the number one is after, can be deduced for any n. And by analytical continuation, one can deduce this formula, just analytically continue by just substituting gamma for n and writing it down. Now, here, what was actually checked, it wasn't, as I said, it wasn't the simulation, rather taking the functional form of the Instanton solution, substituting to the action and calculating this action numerically. It wasn't a simulation. So that's why, and that was done by Monte Carlo, that's why there are error bars. So we were checking with the consistency of our results. Right. So I'm pretty much done. So the conclusions are that we have succeeded in calculating the emptiness formation in polytropic quantum liquids, so extending the known results beyond the free fermionic or weakly interacting bosonic case, something which depends on the parameter. So it's an example of interaction system, and we have seen some interaction features appearing in the shape of the Instanton solution. How this can be extended? There are interesting subleading terms, both for fermions and weakly interacting bosons, which have logarithmic form, and it would be nice to see how the subleading terms, probably by calculating fluctuations, can be obtained. So it would be nice. We didn't manage to find any statistical physics model where the limit shape will appear naturally. I should probably go back and say that in the very beginning that while the emptiness is given by the path integral of this form, the trace can be rearranged in such a way that the emptiness appears as a boundary condition so as a boundary condition which creates this essentially cutting this picture and putting one on top of the other. So it would be nice to have some ideas about any statistical model which can have a polytropic equation of state. So for our results to be valid. In quantum mechanics, it would be nice to have a real-time continuation to the real-time, which will allow to calculate quantum return probability, otherwise known as Low-Schmidt echo. And there is a kind of intriguing connection with disordered superconductors, where the quantity of interest is density of states near the gap as a function of the concentration of magnetic impurities, which is essentially given by the same form as the previous, as free fermionic result. So essentially you have a gap, which is like an emptiness, and density of states goes like 1 over square root. And then this gap closes as the concentration of magnetic impurities plays the role of the imaginary time here. So it would be also, and this is that model was obtained from the sigma model, and we are sort of looking for other condensed matter systems like superconductors, where different power laws, different polytropic index can be used or can be modeled. So yes, so this is yes, I have a final.
Thank you very much for the interesting talk. Are there any questions, comments?
I did not catch. If you have that your interval is given by the sum of two monomials, can you extend it or is it
I haven't thought about it. Maybe it's possible, but I don't really know. I mean, no idea.
Okay. Filippo? Yeah.
Yeah, I'm wondering where does the ground state come into this picture? Because it seems to me that at the beginning you were talking about the empty formation probability of the ground state of free fermions. But like, is it also related to the ground state of these quantum liquids that you're talking about, or it's for any state?
Yes, it's essentially zero temperature calculation. So that's the ground state calculation. But one can, so essentially you calculate the energy of the ground state as a function of the density that gives you the equation of state. So imagine you have I mean, for different systems, it can be different dependence, and we just use this input to calculate the emptiness.
So for finite temperature or other states,
we didn't try. I guess it can be done by simply putting the system on some sort of cylinder.
Okay.
As shown in the first slides, there is a temperature, but we specifically take infinite time.
Okay, thank you.
Thank you. Any other questions, comments?
Yes, no, I was a bit confused. I mean, I'm not sure I understood why you are really talking about interacting system. I mean, on this last slide, I mean, in which sense can one consider that you are looking at interacting system here? Wouldn't we need at some point some kind of Luttinger type of theory to do that really properly?
Well, in some sense, yes and no. I mean, so if I look at the small deviation around, say, rho zero, the system is a Luttinger liquid with Luttinger parameter depending on this polytropic index. And interacting, I'm saying that like, well, gamma different from 3 would, if it's greater, that would correspond to repulsive fermions. If it's smaller, it's attractive fermions. Okay. And very attractive fermions become weakly interacting bosons. But it goes beyond the Luttinger liquid behavior because it really explores configurations where density goes to 0. So it's sort of extreme nonlinear Luttinger liquid. But the idea is roughly yes.
Okay.
Any other questions? Okay, so I have one. So you mentioned the similarity to the case of random matrix theory, right? For such case, there are many works on large deviations, I think, by Satya Majumdar, Gregory, these people, for example. Is your techniques kind of related to that approach or they're completely different?
I think they are related and can be used. This would correspond for the leading terms to the free fermion, free fermion system.
For the free fermion case, they should be related.
Yeah, yes. So one can extend to this random matrix calculation to imaginary time. One can essentially the random matrix calculations, and I mean it's essentially finding that solving like trying to find that slide here. So I would say that this is solving this equation at tau equals 0 is essentially Coulomb gas calculation.
I see.
And all the evolution follows from that. It's essentially saying that one solves this equation with the right past and future boundary conditions by finding a good adjusting the velocity and density in such a way that it goes to the right boundary conditions at infinity. And Coulomb gas and analyticity does the whole job, and this is the well-known parametrics.
Okay. Another question is, does integrability play any important role in your calculations? Hydrodynamic description are completely different for non-integral case.
So that's what was one of the motivation. We don't require integrability. We rather require some analytic structure.
Then if you want to study large deviation for integral systems, you have to modify your theory.
Yes, of course. Well, we are thinking about how to do that in the framework of generalized hydrodynamics, but so far we came up with something which.
Okay, thank you. Any other questions, comments? Okay, if not, let's thank the speaker again. Okay, I think today